Hi, good evening. Mm, Just a minute. Yes, Shreyan, I didn't think of on that. Sorry for it. I read it, but I didn't go ahead. I think I may see it in next week because I am a little bit busy with some other write-ups and all, even if so many things are remaining. Okay, but first, frankly speaking, when I read, I needed to read it for 5 times. I tried to configure it, and I have some typical visualization. So I will reflect on that maybe in end of next week. If not, then before that you ping me. Okay. Yes. Going ahead. Yes. Actually, in my yeah laptop, I couldn't find the window for presentation. So yes. So today we are going to have some typical and very small kind of basic configurations. What I had made a plan accordingly. I think we need more 10 sessions. Let's see how hopefully we get them. But for today, as I planned, there are some typical figures and their analysis. We call them as configurations. There are such many different configurations. Today, we will start those configurations. In maybe tomorrow, I will put more configurations for your additional work. Those are not so much advanced, that I know, but those are also not so much basic. Okay. Because some small observations may lead us to great results. Okay. So let's have, we call them as some configurations. Yes. So here I assume that you know some basics of geometry. Like we have seen, this is our sixth session. So almost now we have uh, means I tried to recognize that you know some kind of basics. And if you don't know the proofs, then I always like to ask you to know the proofs. So basically, our plan is that we have seen Seva's Menelaus little bit. And now, oh, sorry, I was going to sneeze. So after Seva's Menelaus, a little bit we had touched about power of point. We will go with power of point again, then also the radical axis and all. Then we may turn our attention towards some quadrilateral like cyclic quadrilateral, then some typical theorems related with that. Moreover, as we have seen Seva's theorem, Menelau's theorems, related with that we have isogonal conjugates, pedal triangles, Simpson, and their brotherhoods, sim medians and all. That also we are going to see. We have touched homothety. So formally homothety also is going to come. And then we are going to see in between few problems which have come for some typical contests like in Mo or some other of that level. For that I made a plan, and according to me I may require more 10, 11 lectures at least to cover those topics. Here today we are going to have some configurations which are really basics, and I think I'm going to write first of all. So I call it as C1. Okay, it is the centroid, circumcenter, orthocenter, also 9-point circle. It covers so many things. Okay, so basically we know that what is centroid, circumcenter, orthocenter, 9-point circle. The center of 9-point circle is known as 9 center. Okay, so our figure tells us that many times we need to draw a figure again and again, but basically I need to show you. Just a minute. Just a minute. We know that the point of concurrence of all three altitudes is the orthocenter. We also have seen last time, or maybe last to last time, about the similarity of these triangles and the existence of H for the pedal triangle DEF. Let AD, BE, CF be the altitudes. Okay. Then in general, we call A prime as the midpoint of BC. B prime is midpoint of AC, and C prime is midpoint of AB. Okay. Then you know that the triangle DEF is a special pedal triangle. Triangle DEF is a special pedal triangle. I hope you know what is pedal triangle. If not, let me know. Do you know pedal triangle? Don't do Google search now. If you know, let me know. If don't, then let's see what is a pedal triangle. I hope you know that. But if not, then just don't take more time. Okay, Hayagriv requires pedal triangle once again. Good, no worry. See, we know that. I will explain in short. Suppose I have a triangle. Say this is a triangle, and there is a point in the plane of triangle. Suppose the point is here. Then I drop the perpendiculars from that point. Okay. I drop the perpendiculars from that point, and then we get the triangle joining by those perpendicular feet. Such a triangle is termed as pedal triangle of that point. Suppose I consider that point as P. So that is the pedal triangle with respect to point P of triangle ABC. This is our triangle ABC. If our point P is exterior, then we may have the perpendicular feet like this. Then mm, yeah, H is the in center. That is correct, Govind, of triangle DEF. Okay, so, or I call this as, so this is the pedal triangle with respect to this point. When that point P is the orthocenter, so HD, HF, HE are the perpendiculars. So DEF is a pedal triangle for point H with respect to triangle ABC. Here H is the special point that is known as the orthocenter. Therefore, that pedal triangle also termed as the orthic triangle. Such pedal triangle is termed as orthic triangle. Okay, I hope it is clear. Hmm. So for equilateral triangle, we have that, or for any triangle, okay, we get the pedal triangles. Okay, but there is a typical finding that if this point P lies on the circumcircle, if that point P lies on the circumcircle, suppose the point P is over here. It is not on the circumcircle, but let's consider. Then the pedal triangle turns to the line that is known as the pedal line, or also known as Simpson line. We are going to see Simpson line and their brotherhoods in coming lectures. So just I am giving you the information about them. So this is a lecture that we are going to have informations, so many informations, very packed informations I am going to give. I am not going to entertain so many rigorous proofs for now. Just we will have some very typical ideas to move ahead. Okay. So I hope you understood what is Simpson line. So if P lies on, specially on the circumcircle of triangle ABC, and then the pedal triangle with respect to such point P turns to the straight line, that line is known as pedal line of the triangle, or also known as the Simpson line of the triangle. When we observe that, if we have a right angle triangle, then these two are the altitudes, and the third altitude goes over there. And so the pedal triangle with the perpendicular feet of the altitudes turns to the pedal line, and it shows that these 3 points are that circle passes through the right vertex. It shows. So we can cover like this also, because this is a straight line, and so that is a Simpson line. So altitude on the hypotenuse of a right angle triangle is the Simpson line or pedal line on the triangle. Okay, so that is a special case. Means pedal triangle for a right angle, sorry, orthic triangle of a right angle triangle is the Simpson line. Okay, orthic triangle of a right angle triangle is the Simpson line. Yeah, I can write over there. That is a special. So you also can write. There are so many results. What did I say? That if P is a point in the plane of triangle ABC. Okay. Then let PD perpendicular to BC at D, PE perpendicular to AC at E, and PF perpendicular to AB at F. Then triangle DEF is the pedal triangle. Is the pedal triangle of triangle ABC with respect to point P, or pedal triangle of point P with respect to triangle ABC also sometimes it is said. So here if P belongs to the before that I must tell you that if P is the orthocenter, H, then triangle DEF is termed as orthic triangle of triangle ABC. So here there is no need to say with respect to H. When it is said orthic, then automatically it is because of the orthocenter is confirmed. Okay. Then we say that if P belongs to the circumcircle, if P belongs to the circumcircle of triangle ABC, then DEF would be collinear, DF would be collinear. That line is known as Simpson line or pedal line. I leave the proof of these things with you. The proofs are available in some typical books, but I hope we need to work on these proofs. So is there constant Simpson line? Shreyan has a question. Can anyone comment on this, that if Simpson line is constant? Okay, so I would like to listen from the others. So we can say here one more I would like to write. For a right triangle, its orthic triangle is degenerated to the Simpson line. So now it is clear that P lies on the circumcircle. So how many points are there on the circumcircle? How many points are there? So accordingly, we can have the pedal triangle. But if we say that P coincides the vertex of a triangle, any one of the vertex of the triangle, then what will happen to Simpson line? So if I say that if P coincides a vertex of triangle ABC, then which is the pedal line for P? So what would be the pedal line for P? Can you tell? If P coincides a vertex of triangle ABC, suppose it coincides vertex A. Suppose it coincides vertex A, then what would be the pedal line for P, or pedal line with respect to P? Can you guess? Pedal line is the line passing through the perpendicular feet drawn from the point. Hmm? Okay, I leave this question for you. So I think Shreyan, what is your opinion that is there any constant Simpson line? What do you think? Well, okay, which one is that? Can you tell which line you mean be constant? Means if P has a fixed position then, or otherwise does it remain constant if P varies? Okay, P varies and even if it remains constant. What is that? Means you say constant with respect to length or the position. I'm not getting it. Can you explain? Yeah, I'm just waiting for his reply. I hope others are also reading his chats. So can you comment on that? Because I'm not easily getting how the Simpson line goes constant because we are drawing perpendiculars.
So, sir, I mean, for
Um,
any point P on circumcircle, is the Simpson line the same? Like,
oh, that. Oh, no, 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 no. I took the meaning that even if P varies, line say remains constant. Oh, yeah, yeah. See, obviously, what? See, you read this step by step. First, we know that pedal triangle, and we know that from a point to a given line, we can draw exactly one perpendicular. So if P is chosen, then the perpendicular feet are fixed because triangle ABC is fixed. And so the Simpson line for P is always unique. Okay. Yeah, I got the meaning because I took the meaning that Simpson line remains constant wherever the P goes. I consider like that. Okay. Yeah. Coming to the point. So here our configuration is about centroid, circumcenter, orthocenter, and 9-point circles. I must tell you the notation so that wherever we are going to go with that notation, then you understand. Earlier, we have seen about the pedal triangle, pedal line, or thick triangle, the special case of pedal triangle. Moreover, we have some notations which are very common notations like G is the centroid, H is the orthocenter, A prime is midpoint of BC, and similarly the others. Okay. Yes. Sharav says that I don't think a pedal triangle exists when P coincides with a vertex. Yes, you are true. Now just look at this figure. If A is P, then the pedal triangle turns to the line which is AD. Okay. So in that case, the pedal triangle turns to the Simpson line, which is the altitude. Okay. Yeah, that is the altitude. Yeah, Aditya stated that it is altitude. You can chat with everyone so that others also can read your chat. Then I don't have to need the read the chat. Don't have to need to read the chat. Okay. Yes. So these are very common notations. Oh, yeah, I'm just recalling what is remaining or not. O is the circumcenter. Yeah. Uh, According to my memory that I took these configurations in 2019, our RAM TP Raising a Mathematician training program. But, and I am recalling that where Shreyan was sitting there, I took some constructions, not these configurations, if I am not wrong. And those constructions, not our routine construction, some typical geometric constructions. Uh, I had taken. It's okay. So these are the notations. Hmm. The very common things are there. How is it the altitude? Okay. See, from A, how can I draw the perpendicular? The perpendicular lies on the point A only. Okay. And so from A to AB, if we draw the perpendicular to this and to this, the point is the same. And to the other, the point comes over here. So if we join these all, we get AD. That is the pedal line. Yes, Sharav, did you get? Yeah, there is no existence of perpendicular at the same point. The point where the perpendicular comes, that is the point. That's all. Okay. So both perpendiculars meet at A only. I had a fear of that only. Okay. Okay. It's okay. So coming to this, if some notation is remaining, then I would like to tell you the notation afterwards. Okay. See, when we have our triangle, here H is the orthocenter, then O is the circumcenter, and A prime is the midpoint. Then very important result that we have, I may call it as number one, that A prime O is half of HA. This is very important result. Don't think to prove now. I just tell you that mere similarity will help you to prove this. For that, you need to draw the median A prime and consider the triangles where the median cuts. That point you term it as, suppose. Generally, that point is actually the 9-point center, but it's okay. Not 9-point center, sorry. That is another point. So that we may call any point, and you get those triangles like what I am telling. We draw the median. We cut this. Say this point is X. Then we have AHX and OA prime X like that. Okay. So this is one typical result. Then we have that A is the orthocenter of triangle HBC. Similarly, B is the orthocenter of triangle. If I take B, then that is HAC. And C is the orthocenter of triangle HAB. Okay. So looking in the same figure again, I may cut this. If I have, say here, HAB, already HA is drawn, so I consider HAB. Then we need to show that A is the orthocenter, which is but obvious. How? If we extend this perpendicular. So it means that is the altitude from A. It is the altitude. So this point is E. No. So AE is the altitude on BH. AE is the altitude on BH. Similarly, we have BD is the altitude on AH. And so the next altitude comes, okay, So AE is the altitude, BD is the altitude, and this HF is the altitude. Where are they meeting? They are meeting at C, and hence C is the orthocenter of triangle HAB that we have. Yeah, I am explaining but not writing. Sometimes I am not, I'm just going to give some hint. Okay, very typical that circumradii of triangle ABC, triangle HBC, triangle HCA, triangle HAB are all equal. Or we can say that circles, circumcircles of triangle ABC, triangle HAB, triangle HBC, triangle HAC are all equal, congruent. How to prove that? See, remember, all these proofs will remain you as homework. You have to, don't consider them as very elementary results. Try to prove them. These are some step-by-step thoughts. So, okay. Okay. Then very important, yeah, some use the fact that area of triangle is ABC upon 4R. Oh, can be done. Moreover, you can go by angle chasing for the third result. Okay, little bit angle chasing may help us. Then H is the circumcenter. Very important result. H is the circumcenter of the triangle whose sides are the lines through ABC parallel to the opposite sides of triangle ABC. This is a typical, very small result. H is the circumcenter of the triangle whose sides are the lines through ABC parallel to the opposite sides of the triangle ABC. How does it look? Say this is our triangle ABC. Just a minute, I will redraw it. Say this is triangle ABC. If we draw a parallel, then if we drop the perpendiculars, then this is the circumcenter. And actually this fact is used to show the altitudes are concurrent traditionally without using sevas or trigonometric form of seva. If we need to show that altitudes are concurrent, we use this fact that H is the circumcenter of that triangle whose sides are the lines through ABC parallel to the opposite sides of triangle ABC. Okay, proof is very simple. That doesn't go longer. Okay, yeah, going ahead. Fifth, that if X is a point, so we are introducing one point X in the plane of triangle ABC, just for particularness. Okay. And if G1, G2, G3, actually G sub 1, G sub 2, G sub 3 are the centroids, are the centroids of the triangles XBC, comma, XCA, comma, XAB, respectively, then triangle G1, G2, G3 is similar to triangle ABC. This is again a typical result. X is any point in the plane of triangle ABC. Okay, such that triangles XBC, triangle XCA, triangle XAB should exist. That XBC must not be the straight line, or otherwise the triangle is degenerated to the straight line. Then how can the similarity happens? Okay, because if straight line doesn't have like that any centroid. Or if I have the straight line, I can say 2:1 where it intersects, that is the centroid. But that case we do not consider. So XBC, XCA, XAB, those triangles should exist. How does it look? It looks very weird. Maybe. Suppose this is our triangle ABC. I am taking X here, or here, or here, or here, or here, or here, wherever I can. Okay. Yes. So sophisticated, we can take, suppose X is here. Then our first triangle is XBC. XBC. A prime is the midpoint. And suppose here is the midpoint. So if we draw them, so here is G1. I will rub these all. Here is G1. Now our another triangle is XCA. So here is B prime, the midpoint. And say here is the midpoint. Here is our G2. And now we want XBA. XBA. Oh, it is not on that XC. Remember, this is G3. Then it is said that triangle G1, G2, G3 is similar to triangle ABC. Okay. That is the result. How to prove? Just keep in mind. Don't try, because I know it is not possible to think it at a while or in a while or immediately. Try to take these results with you. They will remain with you, and not only remain with you, you will think on them how to prove. Okay. And I would like to listen from our friends if you have ideas coming in your mind recently. Okay. And then I am actually always looking forward from you to add on the results in this list, so that for the next generation, I can share those results. Okay. So don't only take these results. Hmm. Yeah, just a minute. I was keeping charge. Okay, sixth one. It is again a typical. The circumcenters of the triangles A, B prime, C prime, comma, B, C prime, A prime, and C, A prime, B prime. Sorry, not and here, comma. There are four triangles. And A prime, B prime, C prime. So these triangles are taken. A, B prime, C prime, B, C prime, A prime, C, A prime, B prime, A prime, B prime, C prime. Okay. So circumcenters of these four triangles are related. This is very interesting. Are related that each of the orthocenter, each of, sorry, that uh, each is the, sorry, each is the orthocenter each is the orthocenter of the triangle formed by the other three. Oh, that's really typical. Let's visualize it. Okay, so that you will understand. Say this is our triangle ABC. Then A prime, B prime, C prime. Okay, orthocenter, sorry, circumcenter. I am just visualizing it. It is here. It's here. It's here. And it is here. So these circumcenters, that suppose I call it as O1, O2, O3, and I call it as O prime because it is a special triangle, A prime, B prime, C prime. So what does it mean? That O1 is the orthocenter of triangle O2, O3, O prime, and so on. Did you find anything? Did you realize something? Have you seen this kind of configuration earlier? No, I think my figure is misleading, exactly misleading. And I did it intentionally? No, it happened by mistake. But I would like to come back first. Read this. H is the circumcenter. No, 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 no. Sorry. Where it is? Yeah, here, second. A is the orthocenter of triangle ABC. B is the orthocenter of triangle HAC. C is the orthocenter of triangle HAB. Okay, got it. Compare this. Oh, now actually my figure is a little bit misleading because here is the perpendicular bisector. Here is the perpendicular bisector. And here is the perpendicular bisector. This is O prime. Here is O1. Now you can check that O prime is the, oh, I don't know what is it. I really don't know. I am just showing you some little bit resemblance. O1 is the orthocenter. That is to show like that. So I just gave you some vision. You can think ahead. Today we have to go ahead with some more results. Now, seventh result come that H is the circumcenter of the triangle whose vertices are the circumcenters of the triangles HBC, HCA, and HAB. Okay, what is it? So if we have this triangle, say H is the circumcenter, oh, orthocenter, then here H, here ABC, then we have here, what should I say here? I don't know. I will just, I'm not interested in giving the names to the points now. Here somewhere, and this will go like this. This will go like this, and here, so we come over here, little bit like that. So maybe, I'm not sure about it, but it's okay. Yep. And now we need to show that H is the circumcenter of this triangle. Where these points are the circumcenters of HBC, HC, and HAB respectively. You can see that it wanders around the midpoint of AH, midpoint of BH, midpoint of CH. Oh, if I draw the midpoints of AH, BH, CH, then I am going to get the circumcenters of those triangles. And yes, there is something. So the proof is done. I am not, I think I spoke a lot. Did you get? I hope you must. See, these configurations are really very small, but I feel that they are really interesting also. Going ahead. Eighth one now. So we again introduce another point X on the circumcircle. So we say that if ABCX are concyclic, points, and if H, H1, H2, H3, not H4. Are the orthocenters of the triangles ABC, XBC, XCA, and XAB respectively, then AH parallel to XH1 with AH is equal to XH1, and the lines AH1, BH2, CH3, and XH or HX have a common midpoint. Ayo. Have a common midpoint. Oh, what does it mean? Okay, how I said AH is parallel to XH1, actually symmetrically it goes PH parallel to XH2, and that is equal. Oh, how to visualize? Let's see. We have our triangle ABC. Okay, X is anywhere. Suppose X is here. I wonder where it works suitably for visualization. Okay, now H is the orthocenter of triangle ABC. Now I am looking for the orthocenter of triangle XBC, orthocenter. So for that, we have here perpendicular. So the orthocenter comes over here, which is H1. I think it is visible. Okay. Now we talk about XCA. I am not quite serious to draw, but it's okay. And orthocenter comes a little bit over here, which is H2. And now for XAB, if I draw perpendicular over here, so it is H3. Now it is said that this XH1 and this H are equal and parallel. Wow. If so, if they are equal and parallel, then actually it turns to that AX H1H turn to be a parallelogram. Okay, before we prove, we need to visualize. It must be a parallelogram. What does it mean? That HH1 must be parallel to AX. HH1 must be parallel to AX. So if we show AX H1H is a parallelogram, then we are done. Okay, so this is really a typical configuration that helps us to visualize very typical result. Okay, I hope you uh, have these results as a new results, and I am looking forward that you are going to prove them. Okay, you will prove them, not necessarily now, but afterwards. So where were we? Eighth result. Now ninth result comes. That suppose I say that let, oh, not let. So DEF A prime, B prime, C prime, and the midpoints of AH, BH, CH, all these 9 points are concyclic. Okay, so actually this is the 9 point circle. Okay, what does it mean? If I have a triangle, mm, wait, so here A, B, C, these are D, E, F, these are A prime, B prime, E, and here C prime. Midpoint of AH, midpoint of PH, and a midpoint of CH. So these all 9 points are concyclic. That is what our 9 point circle. Okay, you can recall one very typical configuration or result that we have learned already, that AD and OA are always isogonals, and then therefore that D and A prime uh, are isogonal points on DC. So if AA prime, BB prime, CC prime are concurrent, then automatically AD, BE, CF are concurrent and they lie on the same circle, because we have shown that by taking the circle. I think we have done that result on 29th October 2023, and we also made the remark. So what result was there? Suppose the circle DEF cuts. Now here I said circle DEF. Actually, that circle is like this. Aha, it's okay. Then if that circle DEF cuts the sides of triangle again in A prime, B prime, C prime, then those points are that A prime, BB prime, CC prime are concurrent. If AD, B, CF are concurrent, then those are concurrent was the result. Here we have the special case, and that is the configuration of our 9 point circle, what we have done on 29th October or maybe 5th November, I don't know. But according to my memory, 29th October we have seen. So these points are concyclic is a very typical result, very famous result. Okay. And center of this 9-point circle is termed as that 9-point center. Nine-point center, generally denoted by N. Generally denoted by N. Okay, so that center is generally denoted by N. Okay. So the midpoint of AH, BH, CH, we can consider them as, say, UVW. Say this is U, this is V, and this is W. Okay. Then as we know that earlier we have seen that we have stated OA prime is half AH. And so we have another very corollary result. We can say that AU equal to UH is equal to OA prime, which is half AH. And similarly, that we have BV equal to VH is equal to OB prime, that is equal to half BH. And that CW is equal to WH is equal to OC prime, which is half CH. That is actually a corollary result, but just I mention it separately now. Again, we have considered OA prime is half of H. So it is the same. U is midpoint of H, and so. Okay. Just a minute. Then we know that here, yes, O is the circumcenter. Okay, we already have defined it. O is the circumcenter. Not origin. Then we have that OGH are collinear. Okay. Then midpoint of OH is N. Okay. This is a typical thing that OGH are collinear. Actually, this line is termed as Euler's line. That I missed to tell you. Or Euler line also. No need to give the apostrophe S. Euler line. And you know that here uh, existence of that somewhere here. G is here. So actually O here, G here, and here is the 9-point center. Okay. Then it is also clear that midpoint of OH is 9-point center, and here actually OG is to GH is 1 is to 2. Moreover, we have he that OG is to GN is 2 is to 1. That's obvious. Okay. Yeah. See, I am just recalling the facts. Then if I am going wrong, please let me know. How I am recalling that, I am just looking at the figure and finding out, okay, this is happening, this is happening. Some special results are as it is, but these small results, we don't care about them. And many times we make a mistake in understanding them or writing them. So if I go wrong, I always like and I am happy to see my mistake. Okay. Then we have 11th result, that 12th, the four triangles ABC, HBC, HCA, HAB have, okay, Shara wants the earlier slide. Just a minute. Yeah, write it. Actually, I waited, but maybe my time was less. Come on, complete it. Okay, yes, going ahead. The four triangles ABC, HBC, HCA, HAB have the same 9-point circle. I'm not going to draw the figure because you know that H is the orthocenter. Where are HAB, HBC, HCA, and ABC? Now here same means equal. Okay. Uh, that is equal, not exactly the same. Means, oh, not superimposing. Okay. Who can give me the proof of this statement in one line? Oh, that I didn't tell earlier, so you can't. But it's okay. So here, if I tell you that in 11th, that 9-point radius is half of circumradius of triangle ABC. 9-point radius is half of circumradius of triangle ABC, which is but obvious because A prime, B prime, C prime has the circumcircle, which is the 9-point circle of triangle ABC. What did I say? Triangle A prime, B prime, C prime has the circumcircle, which is the 9-point circle of triangle ABC. And as A prime, B prime, C prime is half of ABC proportionate, therefore the circumradius also goes proportionate. And so 9-point radius is half of that. And oh, what about this? If you recall, we have written earlier one thing, it suffices to prove this fact. Okay. Then we have, oh, sorry, that AO A prime U is a parallelogram. Look in the figure. Where is it? O. A, O, A prime U. Ayayo. It is really typical. A, O, A prime U. Like this. Oh, I need to use some different ink. Okay. Almost. Yes, almost. I didn't say yes. It is very simple. And how we got A, O, A prime U? Similarly, we can get B, O, B prime V. What did I say? So similarly, we have B, O, B prime V and C, O, C prime W, that they are parallelograms. Proofs of this, its proof is very, very obvious. It is one line proof or two line proof. Yes, opposite sides are equal. That's true. Correct. Then further we have OG is to GN is OH is to HN. That is very important. This is just because of, see what I have stated over here. Actually, it is like here is H, here is G, here is O. And here is N. So OG is to GN is OH is to HN. That is what the same. Okay. Then what we have, the next fact. If in triangle ABC, angle ABC is 90 degree, then the 9-point circle, then the 9-point circle passes through A. Then the 9-point circle passes through A. Okay, that is very simple. Then if in triangle ABC, AB equal to AC, then the 9-point circle touches BC. That is the base. Oh, because of this touching scene, I recalled one very important thing. Which is really typical, that the 9-point circle of triangle ABC touches the incircle of triangle ABC as well as touches all three ascribed circles. Ascribed circles, also sometimes termed as X circles of triangle ABC. This is really important and very typical result. Means not important, means very attractive result and typical to prove. And when we see that, it's okay. In isosceles triangle, it passes through, sorry, it touches the base, it's okay. But in any triangle ABC that it touches the in circle of triangle ABC, as well as also touches all three ascribed circles. And I am least interested to draw the figure because the figure will go very typical, and by hand it is really difficult to make that accuracy. But you can check this point by using GeoGebra software or any other geometry sketchpad or demos, whatever you have. Okay, Desmos, not demos. Okay, uh, I hope you know X circles. uh, I hope that you know X circles. Okay, yeah, X circle is the circle which touches all three sides externally. So we call it as the ascribe circle. Okay. And in circle touches all three sides of the triangle uh, internally. Okay. So moreover, we know that uh, if triangle is equilateral triangle, then its circumcenter, incenter, orthocenter, centroid, 9-point center all coincide. What I say that if triangle is equilateral, then its circumcenter, centroid, orthocenter, incenter, and 9-point center are all coinciding. They all are coinciding. So if triangle is equilateral, then all those points coincide each other. Its converse is also there. Okay. So any two of it is very typical that if for a triangle any two of centroid, circumcenter, orthocenter, 9-point center coincide, then the triangle is equilateral. Sometimes when we solve the problem, we can figure out the circumcenter and orthocenter. If we find that they are coinciding, we can immediately conclude the triangle is equilateral. Okay. So these are actually the related with our circumcenter, orthocenter, centroid, and 9-point circle. Okay. Okay. So there are more results, but I could recall these all. Now I must tell you one very typical configuration, which is uh, not that much difficult, but see, there are so many different results. Yes, orthocenter. No. Wait. I didn't bring here in center in converse because that is not immediately in our configuration of uh, the name. In the name, we have stated circumcenter, orthocenter, centroid, and now 9-point center. So I didn't take. But you are correct to say that if in center, even if we can say that in center and centroid coincide, then also it turns to the equilateral triangle. Okay. So actually any two of these we can say any of those five. Okay, so I forgot the name of the writer, but uh, long back, more than 150 years back, a person published different results about the configuration. I call it as the second configuration. That configuration is uh, in center and X centers. There are some 70 plus or maybe 80 plus. I forgot the correct number, but there are results without proof. So results are given, we need to prove them. Yeah, and almost except one, two results, all are immediate coming, or we can prove by using trigonometry and our basic knowledge of geometry. Okay. So we are going to develop some typical notation. I wonder that how I am going to draw the figure. I think I have shown you the figure. I can show you the figure, just a minute. Did I show you this figure before this? Just a minute. I am just stopping the share screen. I am going to open another window. Just a minute. It takes a little time. Okay. Yeah, coming to the presentation now. Yeah. As I told you that in 2019, Ram TP, here is the title. So I'm not hiding like this. Okay. So this is in center and X centers configuration. So let's try to read. It is already given there. ABC triangle is given. AP, BQ, CR are the internal angle bisectors of triangle BAC. Sorry, angle AB, BAC, ABC, and ACB respectively. So I term that where the angle bisector meet. Okay, where the angle bisector meet. Like here is A, here is P. Okay, I am going to make zoom in so that you can understand it. Okay, I will explain through this besides reading. Okay. ABC is our triangle. Then I will share this figure, no worry, no doubt about that. Okay, so you can draw this figure on GeoGebra what I had done. AP, PQ, and CR are the internal angle bisectors. Similarly, we name that if I draw here B and I let it meet, say BI3 is going to meet here AB, here, oh sorry, that is AC, then that point would be say Q2. That point would be Q2, like that. Okay, so we have like here the external bisector of angle A meets this opposite side BC in P1. Similarly, B will meet in here Q1, here in R1, like that. Okay, so C will meet in R1. I think, did I give the name or not? I don't know. Yeah, here is R1. Only the Q1 it doesn't come. It is going long back. Okay. So that figure is not So how much part I took? Then where the where the in circle meets, touches the sides, I name them as X, Y, and Z. X, Y, Z. Where the X circle whose center lies on the uh, internal angle bisector of angle BAC, that is I1. Sometimes it also named as I sub A, like IA. Sometimes we also name it as IA. Okay. Then the X circle with center IA touches the sides in X1, Y1, Z1. Similarly, the X circle with the center I2 touches the sides in Y2, X2, Z2, and here X3, Y3, Z3. Now, in terms of what we can find out first of um, all the lengths. I am going to narrate right over here. All the lengths like BP equal to BR, CP equal to CQ, QA equal to O, AQ equal to AR. These are equal tangent segments on from exterior point. Each we can find out in terms of ABC and angles ABC if required. Capital ABC denote the angles. Like I can say that BP is nothing but our S minus B. This BP is nothing but S minus OB. CP is S minus C. AQ is S minus A. Like that. S is the semi-perimeter. S is the semi-perimeter. Okay. Similarly, we have actually area of triangle ABC as R into S. Area of triangle ABC is R into S. Because of this, I recalled one very interesting property that is the proof of just a minute. Just a minute. Yes. See, in right angle triangle, if we have a right angle triangle, say triangle ABC, then its in radius, I is the in center. These are RR. Say it is where the circle meets, those points are X and Y. So this is BX, BY. This is Z. This is Y. Okay. So this CX would be A minus R. So CY is also A minus R. AZ is C minus R. So CY is also C minus R. And then therefore we get C minus R plus A minus R as AC, which is B, which gives us that C plus A minus B is 2R. So the in radius is nothing but C plus A minus B upon 2 if angle ABC is 90 degree in triangle. Moreover, I have area of triangle ABC is half uh, here AB into BC. So that is half AC, which is also RS. And then therefore R is nothing but we have AC upon 2S. Okay. So if a triangle is right angle triangle, then we get this. Now, very simple. If we resemble these two, we have C plus A minus B upon 2 is equal to AC upon A plus B plus C upon 2. Oh, that is twice, so that comes A plus B plus C. Twice of S is A plus B plus C. That we know very well. If I do this product, cross product, then it turns to A plus C whole square minus B square is equal to 2AC. So that is A square plus 2AC plus C square minus B square is 2AC. Great. 2AC, 2AC cancelled. And we get that A square plus C square is equal to B square. Another proof of Pythagoras theorem. Just I wanted to share. It is not a big shot, but another way to get the proof of Pythagoras theorem. Okay. It's a computational proof almost, because we are computing the lengths of in radii in different fashion by using area relation, by using the tangent segments, and so we can prove it. And C plus A minus B upon 2 comes, that is because angle ABC is 90 degree. So in short, coming to the figure again, if we have these all, there are so many interesting results that I is the orthocenter of triangle I1, I2, I3. I is the, this I is the orthocenter of this triangle. Okay. Okay. Hayagriv has a question to this earlier. Yeah, I am coming to that point. Yes. See, AB, the length of AB is termed as small c, and BZ is R. So AZ should be C minus R. Got it? Oh, I said CY. No. Yeah, CY is A minus R. Oh, that is, I said A minus R. Is it correct? Yeah, it is correct. Why? Because BC is A, BX is R, so CX is A minus R. Got it? Yeah. Okay, so here what I try to tell you that if you look at this figure, then you come to know that, okay, I is the orthocenter of triangle I1, I2, I3. Then we can find out each length in terms of our ABC, like length of sides and measure of angles. We can derive half angle formulae. We can derive the typical connections between or among some these sides, like all these AZ1, AY1, CX3, CY3, BX2, BZ2, all are equal. And those all triangles are actually the isosceles triangle, but not similar because their vertex angles are different. There are, moreover, we can find out the length of AP. We have the existence of the harmonic conjugates, like where P and P1 are the harmonic conjugates. So PAP1 angle is 90 degree. The circle passing through PAP1 is termed as the Apollonius circle of triangle ABC. Similarly, we have Apollonius circle on sides BC and AC respectively. And the circle shows us the locus of point A, and that locus of point A such that AC remains the bisector of sorry, uh, I am wrong in saying AP remains the bisector of angle ABC always, where always P and P1 should be the what we say harmonic conjugates of BC. And those harmonic conjugates are like BP is to PC, is BP1 is to P1C, is AB upon AC. So that the ratio of remaining two sides, AB upon AC. And so this Apollonius circle had some typical importance. We are going to see them in our due course. Okay. So I think for today, it is more than sufficient. I will try my level best to put you many configurations with a few questions, but I would like to ask you or provoke you to get more observations from those configurations. Okay. So just wait for some days, or maybe 1 or 2 days I will put it. Till then, we should say now bye bye and thank you and good night.